Hello, this is Dr. Bitla Venu coming in front of you in continuation to my previous session. In our previous session, we have discussed CNC part programming, few examples. But in today's session, we will discuss a few more examples on plane turning, step turning. If possible, we will try to discuss taper turning examples also in this session. Let me move forward to discuss the examples in this case. Then yesterday we are already discussed all this, and let us see this. Yes, this is what the example. Uh, Let me read out the problem first, sample example first. Write a CNC program to produce the diameter of a bar from 40 mm to 30 mm for a length of 30 mm. So initially we have a bar of 40 mm diameter and its length is 80 mm. For 30 mm length, we need to reduce its diameter from 40 to 30. Using some cutting parameters in the problem, they are given depth of cut for rough turning as 2 to 3 mm and for finished cut turning as 0.3 to 1 mm. So during rough turning, this is what the depth of cut, and during the finish cut, this is what the depth of cut. Then assuming the spindle speed 2000 rpm during rough cut and as well as finish cut, then feed rate is 0.3 mm per revolution. Now let us see, even for the feed rate can be assumed differently for finish cut and as well as the rough cut. So this is exactly the problem that we are going to write. For this, we are going to write CNC part program. So now we have a block statement. First block statement tells us about G90. G90 means the absolute programming. Then G95 indicates the dimensioning in metric units. We are following the absolute programming and the coordinates are absolute. That means with respect to one point, these values are going to refer. Then we are giving all the values in metric units. Then we are specifying the feed rate in mm per revolution. So this is, then tool number is 1. So we have to use that. So then tool number we need to use 1. Then you come here and 50 next block G28U00. That means somewhere we have tool somewhere else on the work plane. So that will come to the work 0 location or machine 0 location or the reference point of the machine. So then after coming that tool to the work 0 or machine 0 location, so then we move forward to select the tool, T01 tool with the tool change command. M06 is the tool change command. So after selecting the tool, then we're rotating the spindle in clockwise direction with an RPM of 2000. So M03 is the miscellaneous code which tells the machine to rotate the spindle in clockwise direction at a speed of 2000 rpm. This is what already mentioned in our problem that you can see here. Then as of now, our tool is at reference location, so 00, U0 and W0, and from that point the tool will come to the X41 in rapid mode. Z00 is the rapid mode miscellaneous command, so that the tool will come to the X41. That means exactly, so the total diameter is 40 and exactly 1 mm over a 40 mm diameter, it will come just 1 mm, so that it is 41. Now our tool is at this location. Now our tool is at this location. Let me annotate that also here. Now our tool is exactly at this location. So 1 mm above that. So up to here it is 40 and it is 1 mm. So that means 1 mm is our approach distance. 1 mm is our approach distance. Okay. So I'm moving this here. So 1 mm is our approach distance, and so this is in rapid mode. Somewhere we have tool, machine 0 or work 0 reference. So at this location, and the tool will come to at this location. I mean, 41, 1 mm just before to the workpiece. So then we move forward, then the tool will move forward with 35 mm diameter. Now, I mean, with 41, okay, 41, and at this location the tool will come. So the tool will come x35, means the tool will move to x35 here, x35 here, then at a gap of 1 mm here. At a gap of 1 mm, we can provide at a gap of 1 mm. Otherwise, 35 mm, the tool will move 35 mm here. Then this is what the step, tool will go 35 mm. So then the depth of cut is 5 mm here. That means the depth of cut is 5 mm we are giving here. So not 5 mm, it is 2.5. If we give 2.5, the diameter reduces to 35 first. The depth of cut is 2.5 mm here. So it is, now we are at this location at a distance of 35 mm above the or the diameter wise. So after coming 35 mm, the feed rate were specified f 0.1. So then the tool will move negative z axis 30 mm. That means with that depth of cut, the tool moves here. So the tool will move with a feed of 0.1 mm per revolution. So now the plane turning will take place in single pass at a depth of cut 2.5 mm for a length of 30 mm in, in linear mode. In a linear mode, the tool will move so that the turning action takes place with a depth of 2.5 mm. So this is the reducing. In turn, the diameter reduces from 40 to 35 because the depth of cut is 2.5. So overall, the diameter of the workpiece reduces from 40 to 35. So now, so let us move forward. Let us move forward to see. Let us see. Let us move forward to see. Of course, let me move the here. Uh, Let me erase this also. Let me erase what we have did as of now. Then now the objective is to reduce its diameter from 35 to 30. So by giving different feed of rotation or by giving uh, uh, different spindle speed. But in this case, I'm not going to vary the spindle speed. And let me close this also. So now the diameter of the 40 mm of this block is reduced to 30 mm, 35 mm. So now the second pass, during the second cut, we need to reduce by giving the same depth of cut from 35 mm to 30 mm diameter. Now let us see. Now we are exactly at this step. We are completed the plane turning operation for a length of 30 mm. Now 35. So this was reduced to 35 mm. Now just you come back. So after coming here, now we are at this location. The tool is at this location. So 1 mm above this. So now you come back. Now you come back to 1 mm back. Now we come back to 1 mm, and so now we are 35 actually. 36 we will back. 36 we will back, and 1 mm here. 1 mm here. After 1 mm, so we will come back 36, then 1 mm here. So we will move here. So 36, so 1 mm backwards uh, and rightwards we have to move. Now we have minus 30. So we will move 1 mm, 1 mm Z positive directions. That means we are providing 1 mm clearance distance between the face of this block and the tool. So with that 1 mm distance, we move forward to give depth of cut. Now you see here. So now our tool is at this location, just 1 mm, 1 mm in Z axis direction, Z positive direction. That means exactly in front of the workpiece, we have 1 mm clearance, that is Z positive, Z1, as you can see here. After moving 1 mm distance, then we move forward by giving depth of cut. Now we move forward 31 mm. So now we move forward 31 mm. Then yes, exactly, now we are at 31. Then 31. Then the feed rate. So now we can provide the feed rate. So okay, 31 mm. Now let us move backwards. Now let us move backwards. So now let us move backwards with 30 mm. That means negative z axis. So actual turning action takes place with 35 to 31, means 4 mm. By giving 2 mm depth of kit, we are reducing its diameter. So that means 35 to 30 mm. In this step, we are reducing the diameter of the block. So initially we have 35 here. By giving 2 mm depth of cut, so you can see here x31, 35, 31. Then we move backwards, that means z negative direction in linear mode. The actual cutting action takes place here, that is z minus 30 with a feed rate of 0.1 mm per revolution. This is also rough cut and this is also rough cut. Now finally, to bring it to the 30 mm diameter, again there is 1 mm material left on this. Now we are at 31. Now the diameter of this block for a length of 30 mm is 31 mm. We need to reduce the diameter of this block, again 1 mm depth. So now you can see, now you come back. So now we will come back to 1 mm. That means we are coming back to 1 mm here. 31. So we moved to 30. The next 32 means 2 mm coming back here. Now we are coming back 2 mm back. Then we are coming z minus 1 here, z minus 1. Okay, so that means uh, uh, we have again 1 mm clearance distance. That means our tool is 1 mm in front of the face of the workpiece. Then we move actual depth of cut. So actually it is 31st. Then we move towards x-axis 1 mm. So that means 31 to 30. So our depth of cut is 0.5. Then we move leftwards minus 30. So minus 30, so that the 1 mm which is left on this block will be machined in finish cut with a feed rate of 0.05. So this is exactly the finish cut. In 3 cuts, we are performed turning operation in 1 pass. In first part, the diameter of this block 40 mm will be reduced to 35 with 2.5 mm depth of cut here. Then the 35 will be reduced to, in the next pass, 31 with 2 mm depth of cut here, with 2 mm depth of cut. Then the leftover 1 mm depth of cut will be given in the final stage, that is called finish cut, towards negative z axis, so that to perform actual cutting action on the work component or the workpiece. So now this is what in 3 steps we are reducing the diameter. So in first step we are reducing, in first cut we are reducing diameter 42. 35, then 35 to 34, 31, then 31 to 30. Finally, our required dimension is 30, that we can see on this. Then finally, we are moving towards the reference location U00 and W00. Then we are stopping the spindle, and then we are stopping the program. So this is what uh, the simple program to reduce the diameter of, simple turning program to reduce the diameter of a component. Initially it is at 40 mm diameter, then it is reduced to 30 mm in 3 cuts. One is with 5 mm depth of cut in first cut. In the second cut we reduce it to 35 to 34, then from 31 to 30 in final stage with a feed rate of 0.05 mm per revolution. This is what the program for reducing a simple program for turning operation. Now let me move further to see one more program similar to this. Now let us see, here is one more program. Let us see one more program. Write a CNC program to machine step turning. Now we have As in the previous problem, we have seen a simple program to reduce diameter in a single step we have. But here we reduce the diameter initially for a length of 30 mm, for a diameter 22.5. Then we reduce the diameter of the same block to 17.5 mm for a length of 20 mm. So using some spindle cutting parameters like the spindle speed in rough cut and finish cut, that is 2500 rpm, depth of cut for finish turning as uh, rough cut turning as one finish turning 1 mm to 1.5, and for rough cutting 1.5 to 2.5. So in all the process, assume feed rate as 0.5 mm per revolution. This is what the machining data that is given to us, and the dimensions of the block and the skeleton of this diagram can be shown in this figure. Then let us see that G28, then we are moving the tool to the reference location, U00 and W00. We can, if we want, we can use end of the block, otherwise it is not necessary. In the previous example, we have not specified end of the block. So in this case, we are specifying EOB indicates the end of block. Now N10 and the next block, we are changing the tool T202 tool. We are selecting the tool. So M06 is the command used to change the tool. So we are changing the tool. Along with this, we might use M06 also here. M06 is the command used to change the tool. So that means this is M06. So tells us to change the tool, and the tool is 202. So tool we are selecting 202 tool with this miscellaneous command. So after changing the tool, then we are specifying the constant peripheral speed, then along with this metric units, feed rate. So those we need to specify here. Similarly, in the previous example also. So in the previous example, so we have seen M97, M94 we are specified. M94, let me move back. M90, so in the previous example, let me go back to the previous example. So 91 we have to specify. 91 we have to specify. Then 90, 71, 95. These three are also needs to be specified. G90, 71, 95. G90 indicates the uh, absolute programming. G90 indicates the absolute programming, and G71 indicates the dimensioning in metric unit. G94 indicates the feed rate in mm per revolution. So these 90, 71, 95. Okay, 90 is the absolute programming, 95 is the feed rate we are specifying, then 71 indicates the metric unit. These three also needs to be indicated in this example. So now let me move backward. Let me move further. So after specifying, these also needs to be specified here. So but exactly here we need to specify N2 and G71 indicates the metric units, G94 mm per revolution, and G90 is in absolute positioning, absolute dimension. So these three needs to be specified here. Okay. So after changing tool, this tool also needs to be used along with the tool change command. So that is M06. So we have specified the metric units, absolute positioning, then metric units, absolute positioning, metric units, feed rate in mm per revolution. This is mm per revolution, and this is absolute. This is absolute dimensioning. Then G71 indicates the mm per revolution, absolute. Then this is the metric units. That means we are specifying the mesh to metric units. So whatever the values are the dimensions that we are specifying specified in this program indicates the metric units. Okay, we are specifying mm, so that means all the values should be in metric units only. So now let me move further to see the other. Now initially we are moving tool to the X27. Now basically this is 25 mm diameter. We have 25 mm object we have. So the diameter of this component is 25. So then that needs to be reduced. That 25 mm needs to be reduced to 22.5 mm first for the entire length. So that can be, so now initially I am moving tool to X27. So exactly 1 mm above the 25 mm diameter. So initially we have 1 mm diameter over this diameter. So exactly 1 mm just before the uh, raw diameter or the raw component we are moving. So X 27, here it is 2 mm. Okay, initially we have 25 and it is 2 mm. So after moving 2 mm, then I am also giving 2 mm further to the Z positive directions. That means X is 27 and Z is minus 2 here. 27 and minus 2 here. So then I move further to give depth of cut as 1.25 because I need to reduce the diameter, right? I need to reduce the diameter from 25 to 22.5, 2.5 mm material I need to reduce. I need to reduce the diameter from 25 to 22.5. So I'm giving 1.25 mm depth. So that means the tool needs to move 22.5. Initially we have 25 and the tool needs to move 22.5. So that means the depth of cut is 1.25. In turn, it reduces on both sides. It is a diameter, so that the diameter reduces to 2.25, 22.5. So then I move backwards to reduce the diameter for an entire length. For an entire length means initially I need to reduce. This is not 30. So please, this is for an entire length means it is 70 mm. So this is 70 mm. So because it is 30 and it is 40, this is 30 and this is 40. So for an entire length, we need to reduce the diameter for entire length. So that is what. So this Z value needs to be 70. So towards negative direction, towards Z negative direction, the tool needs to move. So that the diameter of the raw component or the raw bar or the reduces to 25 to 22.5. So now my next step is to reduce the diameter from 22.5 to 22.5 to uh, 22.5 to 17.5. So now the overall is 25 for a length of 30 here, for a length of 30 here, of course. So here it is 30 only. So please make a correction that here this is take just eraser here. I repeat this. I repeat this. Then let me move further. Now it is 22.5 is only not for 70. Please make a correction. It is for the length of 30 only. So initially we have 25 bar. Even in this case also we have 25 bar. Here the diameter is 25. We are reducing 22.5 for a length of 30. So that here the length of the bar is 30. That is absolutely correct. Please make a correction here. So after reducing the diameter from 25 to 22.5 mm for a length of 30 mm, then my objective is to reduce the diameter from 22.5 to 17.5. So now you can see. So in one step, I am not going to reduce the diameter. So initially I will give 2 mm depth of cut. So if I give 2 mm depth of cut, the diameter reduces to 18.5. Then I will finish cut to reduce the diameter from 18.5 to 17.5. So now let me move further to see that. So now I am moving back. So exactly now I am at this location. After turning Z minus 30, then X is 22.5. So Z30, X 22. I am moving back 2 millimeters. Exactly here, I'm moving back 2 millimeters. Then along Z direction, I'm moving along Z direction. I'm moving 2 units. So that means now you have. I'm coming back 2 units along Z direction. So positive Z axis 2. So that means to overall distance moved by the tool is 20 plus 2, 22 mm the tool is going to travel. So the tool is going to stand behind 2 mm in front of the workpiece, 2 mm in front of the workpiece at a distance of 24.5, exactly 24.5. It is exactly 22.5 and 24.5 and 2 mm in front of the workpiece. Now I need to give the depth of cut. So after standing that piece, now I move forward to 18.5. That means 2 mm depth of cut I am giving. So 18.5 I am moving forward with the same Z distance, that is 2 mm clearance between the face and the tool. Now the tip of the tool is at a point of 2 mm along Z axis, and along X axis it is 18.5. So now I move backward along negative Z axis, that you can see here. So minus 20. So initially we are moved to 30, but now we are moving towards negative Z axis for a length of 20 mm, because we are reducing the diameter 17.5 for a length of 20 only. So I'm moving 20 mm backwards, but that means negative Z axis. Now the diameter was reduced to 18.5 in linear mode I have moved. So now my tool is at this location. Our tool is at this location at 18.5. So now I come back 2 mm, that means 20.5. Then I move backwards to 2 mm in front of the workpiece, that you can see here, 20.5 and 2 mm in front of the workpiece. Then I move further to 17.5. Then with 2 mm clearance along Z axis, I move further to 17.5 by giving 0.5 mm depth of cut. Now you see here, now exactly 17.5 and 2. The tool is in front of the workpiece, 2 mm along the Z axis, then 17.5 along X axis. So now my intention is to complete the pass by moving this tool in a linear mode for a length of 20 mm. Now you can see here, for a length of 20 mm along Z axis, then with a diameter of 17.5. So that completes the final cut. Then I am moving tool to U00 and W00. That means reference point. So overall in this case, I have used 3 cuts. One is in a single turn, I have reduced the diameter of the component from 25 to 22.5 for a length of 30 mm. Then I have reduced the diameter of 22.5 to 17.5. Initially, 22.5 to 18.5 by giving 2 mm depth of cut. Then I have reduced the diameter from 18.5 to 17.5 by giving 1 mm 0.5 mm depth of cut. So in this way, this is a simple program. You can write a simple program by giving the parameters, cutting parameters. Now let me move further to see. Let me erase all these now. Then I move forward to see one more example in turning operation. So then I close it. Then I move forward to see. So we have one more example here. Let us see. This is also similar to the previous example. So I will move fast in this case. So now we have a block of diameter 55 mm block. Initially the block is 55 mm diameter. I can reduce the diameter from 55 to 50 mm. Initially I need to reduce for a length of 40. In single pass, I can reduce by giving 2.5 mm depth of cut, 55 to 50 in one pass. Then I need to reduce 50 to 20, possibly by 3 passes. So assuming the following cutting parameters: speed of the spindle as 2,500 RPM for all the passes. Then depth of cut should not exceed 5 mm. Feed rate is 0.5 mm per revolution. This is obvious, we require that. Then I need to specify whatever the values, G97, G90, G71, I need to specify here. Here also, I require one more specification. Initially, I require one more specification. So N01, then I need to specify the values also here. N91, then G91, then G71, then G95. So G95 indicates the feed rate in mm per revolution. So feed rate in mm per revolution. Then G71 specifies the metric units. So then what is it? G91 indicates the absolute positioning. So these three must be specified in this program at this location. So then after specifying these G codes regarding the tool movement of the regarding the movement of the tool, then I specify the tool to come to the reference location. So U00 and W00. Then I change the tool. So then I change the tool by using command M06 T01. So this needs to be inserted here, M06 T71. So after I have selected T01 tool, so then I move forward. uh, G97, of course, I have already, of course, G97 means specifies the speed of the surface spindle speed. The spindle speed is throughout the cutting, its speed is constant. So that is what this G97 tells. Next, here also, I need to specify the direction of the spindle. So M03. So I am starting the spindle, then I am rotating the spindle with clockwise direction. This is what we need to specify along a spindle. Then feed rate we have to specify. Of course, the spindle is rotating with M03, that I have already specified here. Then I'm moving tool to X50 and Z2. So initially X50, this is exactly the 50. This is exactly the 55. Then I am moving 50. Then I am moving 50 at this location. Z is 2 units. Here this is 2 units. I mean 2 mm along Z positive axis. Then X positive axis. This value is 50. I am moving. Okay, 50. I am moving 50 mm. So that the depth of cut is 2.5. So I have moved to 50, X50 and Z2. Then I am moving leftwards for a length of 50 mm. So actual cutting action takes place here in linear mode, that you can see here in linear mode. So in this case, the finish cut with the depth of cut of 2.25 millimeters depth of cut, and hence the diameter reduces from 50 to 55, 2.5. So you can take this as 2.5. So the diameter reduces from 50 to 55 millimeters. This is what happens in this case. So now let me move further to see the remaining cuts. In first cut, we reduced the diameter from 55 to 50 mm for a length of 40 by giving 2.5 mm depth of cut. We are reduced. Now let us see. So now I am coming backwards. So exactly now we are at this location. Our tool is at this location. So after cutting, after reducing the diameter from 55 to 50, our tool is at this location. Now I am coming back to 2 mm. That means 52 I need to come back, 2 mm backwards I am coming. Then I am moving. So initially at 40 only. So 52 to again I am coming back 2 mm in front of the workpiece here. 2 mm in front of the workpiece. That means in front of the workpiece we have clearance that is 2 millimeters. Same 52 mm diameter at a distance of 52 mm from the axis of the component. So now the next step is to give the depth of cut. So I am giving 5 mm depth of cut here. 5 mm depth of cut here. Yes, you can see here 5 mm depth of cut. 5 mm depth of cut. Then I move backwards for a length of 20 mm. You can see here for a length of 20 mm. You can see 20 mm. So now exactly. So now we are at this location. at this location. So now 20 mm backwards, the diameter reduces to 52, 50 to 40. So the diameter reduces to 50 to 40 here. So now I come back. So exactly at this location I am here. I am coming back 2 mm. I'm coming back to 2 mm. Then I am moving 20 mm. Then I am moving 2 mm. Then I am moving 2 mm Z positive. That means I am at this location. I am coming back. Then I am moving here 2 mm. Z positive exactly at this location. So then I move backward. Then I move frontwards to reduce the diameter from 42. 42. I'm moving backward. 42. Let me go back. Uh, so then I am moving forward to reduce the diameter from 40 to 30. Now you can see here 40 to 30 I can reduce with 5 mm depth of cut. So 40, I'm giving 42 here. Then I'm moving X 30 mm distance here, 30 mm. Then I'm completing this path. So this completes. I mean, in this step, the diameter of the workpiece reduces from 40 to 30. Okay. So by giving 5 mm depth of cut, this is also termed as rough cut. Then 32, the overall dimension that we need to reduce is 20. So one more step we require. So then I am coming back 30. So 50 to 40, 40 to 30, then 30 to 20 we need to perform. So then I am moving backwards 2 mm. I can see here 32 backwards. Then Z towards Z positive direction. That means at this location from here to here Z positive. Then Z positive is here. Then Z positive is here. Of course, Z positive is here. Then X20, I move leftwards X20 with an X20 Z negative direction. I move backwards here, Z negative. So the diameter of the workpiece reduces from 30 to 20 in this case, 30 to 20 in this case. Now you can see. So I'm coming backwards 32. I'm moving, even Z also I have given some clearance. I'm moving towards 20. Then I am moving leftwards to perform the turning operation for a depth of, for a length of 20 mm. Z negative 20 means this is actually the length. So in this case, we are moving leftwards. This is what happens. So G01 is the code for linear movement of the tool. Normally, this is used in all the turning operations. G0 is used for ideal movements of the tool where we require the rapid movements of the tool. That means in that case, the turning action will not take place. So finally, after reducing the diameter, of course, in this case also, if we want finish cut, in all these, we are performed. First case only the depth of cut is 2.5. It is a finish cut. Even this step is also can also be splitted. So instead of giving 5 mm depth of cut, we can give 4 mm depth of cut first. Then we can give 1 mm depth. If we give 4 mm depth of cut, so the diameter reduces from 30 to 28. So then we can give in the next step from 28 to 28 to, so I mean it is 32 to 28. Okay. So 30 to 20 means 32 to 22. It comes to 30 to 22. So if we give 4 mm depth of cut here, the diameter reduces to 30 to 22 instead of 20. So here we have 2 mm depth of cut that we can cut in finish cut. So you can see here that we can cut in finish cut like by giving 1 mm depth of cut. So by varying the speed, we can get the finish. So this is a simple example. So I have not given any finish cut here. So this finish cut can be performed here at exactly at this location for accuracy, because this is the final cut. We need to provide the finish cut also. That is also very, very important. So in this case, the finally, after cutting all these steps, the tool is coming to the reference location. Then we are stopping the program. Then we are stopping the spindle. So M05 we need to specify here, M05. So here exactly we require M05. So which is going to stop the spindle. Then this is going to stop the program. So these two are must, and these two in any of the program, these two steps are very, very important. And next thing is the next case, this step is also very, very important, like specifying the absolute dimensioning, in which what type of dimensioning we are giving here, whether metric or the other types of units. Then whether the dimensioning is absolute or incremental, the coordinate values that were specified here is absolute or incremental. In this case, in almost all the cases, the absolute positioning is given. This is simple to understand. Okay. So that we need to specify. Then the in what way we are specifying the feed rate, that also we need to specify. Then after giving all these parameters, we need to start the spindle in clockwise or either anti-clockwise direction. Then we have to select the tool. After specifying this, we need to select the tool. So by using M6 command, we have to change the tool. So exactly you can see here we have T0101 here. So along with this, we have to use one miscellaneous command which specifies that to change the tool, which is specified along with this. So by using M06, we have changed the tool T101. So after changing the tool, we specify the constant surface speed or else S parameter. And along with this also we can specify the rotation. It is clockwise here. Then feed rate you can specify here at this time itself. Then this feed rate will be continued unless to vary in the next pass. Suppose if we want to vary the spindle speed, or the feed, you can vary at the cutting time itself. So example like this, if we want to vary the feed rate here, feed rate exactly during this stage, along with this Z axis, Z parameter, we can also specify the feed rate exactly at this location, at this location, at this location itself. We can specify the feed and we can perform. Even the speed also we can specify along with the this block. Even block can be. So at that instant, the speed varies. After changing the speed, we can perform the cutting action. This is also a very simple example, similar to similar problem, which with this you can write the programs. Let me move backwards to see what we have seen as of now. So we have done the similar problem here. But it is better, I'm suggesting you that better to take some finish cut, rough cut first, and finally we can leave some portion of the material on the component for 1 mm or 1.5 mm, at least minimum 2 mm we can keep for the, we can reserve for the final cut or finish cut by giving less depth of cut, by giving less feed rate. So very small feed rate, very slow speed rate, we can reduce, we can get the good surface finish. So better to split the component turning or the machining into rough cut and finish cut. During the rough cut and finish cut also we can specify the depth of cut in during rough cut and finish cut. Then we can also specify the feed rate during during the rough cut and finish cut. This is better practice to write the programs in that way. Then it is better to change the spindle speed also during the rough cut and during the spindle speed. This parameter, speed parameter, needs to be varied. So that is also good practice to vary the spindle according to the type of the spindle speed varies according to the type of material that we are machining, accuracy that we require, then how much feed we are giving. All these are the cutting parameters plays a crucial role in the machining process. So while selecting these feed rate, speed rate, then depth of cut is very, very careful, and all these parameters needs to be selected from the process planning. So as per the standard values, we need to proceed further. So this is better practice to refer the standard data book or process planning data to machine. So irregular values, if we provide the irregular values, definitely that is going to create the, I mean, improper machining. This is what my advice. So let me go back what I have seen in the previous problem. In this problem we have seen a simple machining here. So in the previous problems and in this problem we can see the difference. In the previous problems I specified indoor block here, but here it is not necessary to specify indoor block. And even if you want the common coordinates, so that need not be specified here. But however, the programming format and syntax is little bit varying, and the G codes are overlapping between one company to another company. So in one company, G code, however, 95 to 96% codes, G codes and M codes are same in all the different commercially available softwares, commercially available missions outside. So we must be very, very careful, and we must be familiar with the codes which are specific to the mission. So every mission is having some specific codes, and even the values, the designation or the meaning of the, or the function of the M code and G code may also vary sometimes. So I suggest you to go through the mission manual and standard CNC programming manual, compare it, and according to that we need to write the program. However, some of the codes may not match with the codes that are specified in these programs with the standard textbook, standard CNC handbook, but this is actually the structure, and the G codes and M codes are some extent specific to the mission and as well as the software available. So we must be very, very careful by selecting the G codes and M codes, and while writing the program, we must be familiar, which are specific to that mission, which are familiar with the codes. Some codes are specific to that mission. We must be familiar with all those. So with this, I close the session, and in the next session, I will discuss the problems on the taper turning. We will see the taper turning problem in the next initially we combine this taper turning and plane turning in this problem. Then I move forward to see the taper turning. In this case also, I'm moving the tool, just simple movements of the tool. Then in this case also taper turning and plane turning. Then taper turning at the end. So this is what in this session. Thank you one and all for this. And in the next session, we will discuss few more examples. And thank you one and all.